how did you decide that what is the optimal algorithm? How does your algorithm perform, quote unquote, something that is optimal?
For path planning, we chose the breadth first search algorithm, which gives a shortest path. There are other algorithms which give shorter paths than this, such as the A-star and etc. But the reason why we chose breadth first search was because the number of it gave paths with less changes in direction. If we take into consideration A-star algorithm or any other more algorithm which give shorter path, they give Manhattan distance, which includes a lot of turns. So in order to tackle that problem, we chose breadth first search algorithm to.
How did you choose this robot? Basically, what were the design considerations for the robotic arm?
Reason for choosing an articulator manipulator was that it consists of all revolute joints. So if we want to realize this manipulator in real life, the transition from simulation to actual hardware would be easier, and the constraints which would be coming in terms of friction identification for the real hardware and making computed torque control or some kind of impedance controllers for the robotic arm. These issues would be easily tackled in actual hardware if we have a revolute joint instead of a prismatic joint. Also, the workspace which is provided by the revolute joint was considerate enough, and it was able to cover all the 3 pods which were present in one room. We were wanting to use the last link 2, which was the 3rd joint, and we were planning to rotate it completely to the other side so that the berries would be easily dropped into the collection box. If we had chosen a prismatic joint, then the base joint would have to rotate, and then we would have to drop the berries into the collection box. So that would have costed us some time in terms of computation of the inverse kinematics for that maneuver. So we opted to go with a 3R articulated manipulator for the completion of the theme.
Could you tell me what are the limitations of your design?
The payload would be one big consideration for our robot's design, and also depending on how the payload changes, the torque which is provided by these motors would also be another consideration. So if the payload is heavier, we would need more higher torque motors, which would cost more, and also the encoder's resolution, we might need to opt for a different sensing technology other than optical ones, maybe a capacitive one or a magnetic sensing technology for these encoders. Our design is considered in such a way such that we want to place all our motors on the base of the joint. So the base link will consist of all the motors, and then we would be using power transmission elements such as a timing belt and a timing pulley to transmit the motion of individual motors to each of the joints.
When you're putting it in your trough, in your deposit boxes, you deposit it from a little bit of height, it drops in and then it tumbles onto the other side.
We had tested a few times, and then we had come up with a trial and error mechanism for developing this optimal height from which we were able to avoid this issue. But if we could maybe slightly increase the barrier height, which was dividing those deposition boxes into 2 compartments.
Your center obstruction height was actually less. So, and they were, I find it to be quite interesting that you were actually putting it like this, so that they could actually, you could actually disperse them from the sides.
Yeah.
But having said that, the central barrier was pretty low. So if you were having, let's say, a deposit of 5-6 berries, ultimately they will almost approach the height of the barrier. So then there is a chance it could tumble on the
Yes.
So that is one of the limitations.
Everything which we designed in SolidWorks, and after importing it into Coppelia Sim, one of the major issues which we were facing was the vibrations of the parts, and eYRC team had helped us. We didn't initially know that the inertia has to be above a certain level before the Coppelia Sim physics engine can properly solve the dynamics of the system. And one of the challenges was to make our design simple enough so that the dynamically shaped objects which Coppelia Sim would create from our basic design were not too complicated. and that they could be represented by simple physical dynamical shapes for which the physics engine would be able to solve easily.
Could you kind of wonder as to why in a simulator the motors would behave differently? I'm sure that they've not programmed them to sort of have a random element in them, but there's something about the way that these things are implemented that causes this drift in values. Have you seen when you look at your GPS device that you seem to be jumping around 5 meters here, 10 meters there and all that, right? Could it be a related problem?
Do you not think that you are actually hampering the reach of the arm by keeping the baskets in the front? In a way, either you should keep the baskets on the sides or you should keep it on the back. Why should you keep it in the front? Because it will actually hit it. Okay, even if it doesn't do it, because considering the design problem, it is not the part of design problem. So even if we bypass it, then you are limiting the reach of the arm. You see, your board should be towards the end so that it is able to reach farthest. When you are actually solving these problems real life, when you want to move from one room to another room, I want to move from one room in my apartment to another room. I don't move like this. I don't move like that. I move in a diagonal way. I see the most optimal path. We want you guys to understand and accept the way human movement moves and accept them as potential challenges and incorporate them in your problems. Why not?
Typically, all real-world systems are essentially jittery, and you will have to first model how this robot moves. Maybe you can create a noise model, and you can design according to that. Maybe a window around it, a circle around it, through which it should pass. I mean, the whole circle. You don't really just take care of the size of the robot, rather you take care of that circle around that robot. The entire circle has to pass through the entry or exit. Since you are making the diagonal movement inside the room, why can't you make that diagonal movement outside the room as well? The answer that was given is that you are colliding with the room, with the walls of the room, but you don't really need to travel all the way towards inside the room, because after the design is done, so you already know the coordinates of the rooms, and you can design to go diagonally to the nearest point through which you will enter. So in that way, you will not be colliding with the walls, right? So you can go to the nearest point. So just before the main door of that room, there is one QR code, right? So you can go diagonally to that QR code and then make the entry as you are doing currently, rather than going via this Manhattan path, which will be taking longer and will cost you more time.
The basket that you're holding, it's held up in the air, right? And you're holding it with the arm. How do you communicate to the basket to open left or right? Imagine a real basket, right? You need to have some electrical connections and open up the left or right part of this. So since the entire basket is picked up, and the only way to pick up the basket is from that ball that you have on the top. So you need some electrical connection going to that basket. I mean, are you kind of assuming that's wireless, or have you thought about that?
Whenever you throw something, even if I throw a pen, it will bounce, isn't it? It will always bounce.
Yes, sir.
And so goes with the fruits also. Either they'll bounce or they'll squish. So whenever we are throwing it, we usually prefer the fruits kind of a thing, which are a little perishable and soft kind of. We should throw them from a little lower height, or we should place them from a lower height, so that they shouldn't roll over, they shouldn't tumble, they shouldn't bounce, they shouldn't get squished. It's a very fresh breath of air, seeing so many students coming up with interesting solutions, interesting both in terms of their design, in terms of their approach, in terms of trying to solve a complex technical problem, but with a breath of fresh air, as I'm just saying.
It's not about the final process or final product for me. It's more about the process that you guys went through. So I was trying to get to that through my questions. And it seems that you have spent considerable time thinking about this problem, reaching out for resources, going through them, and actually testing out your solution. So those sort of iterative process is where the learning actually happens. And you've wonderfully used the simulation platform. You've used the resources provided to you by eYyantra. And more importantly, you've been able to do all this within the pandemic, within the lockdown situation. In spite of, and I'm pretty sure you all have been sort of tackling your own personal challenges at your level. So balancing that with your college and doing this project, I think is a phenomenal achievement in itself. So that's a big win for everyone. Whether you win the competition or not, you've already sort of won that journey for me.
All this stuff that you are thinking that you're getting out of this competition is a complete head fake. Head fake is in US, if you're playing a football, right? So there is a person in the front who kind of looks in one direction, and then rest of the team in the opposite side thinks that the ball is going to be thrown in that direction, and everybody runs in that direction. So this process that you're going through right now is a complete head fake. You think that you're learning how to do something like in a competition, technical stuff, right? But there's a bigger thing at stake over here. One of the biggest things you are missing out, and you're not even realizing it, I would say, that you're learning out of this competition is how do you work with each other? And I think that's the biggest takeaway. Having been in the industry for so long, I think, all of you are extremely intelligent, okay? You will figure out a way, technical way to solve this problem, that problem. There is no doubt in my head that, we don't have to give you confidence that, oh, we are from IIT, this, that, right? All of you are capable, okay? It's just that how do you open up to each other and how do you draw upon each other? And that's something beautiful that I saw in today's competition. All of you were, I was trying to poke in the team members, right? Hey, let me see if this person can answer that. And the intent was very different. Intent was, hey, can you hold each other's back, right? If you're put in a corner. And I saw that beautifully done today. And I was very impressed how all of you performed as a team member. In real life, that's what it's all about. It's not the solution. It's how do you get there and how do you make that path pleasant and enjoyable. And I think all of you were kind of saying the same thing. The learning and all that stuff is a byproduct. It's a positive byproduct of the process, but then all of you were working together as a team, which was just great to see. These are 6 different startups that could come out. They don't have to be related to computer science. They could be anything. And all of you could take different roles, complementary roles in whatever you do. So I wish you all the best. And I wish you that you fail a few times and then come over that failure with a bang.
We also teach robotics. Robotics is just a vahan with which to teach many more skills. And I think this teamwork is one of them. All those things we call soft skills, which are not soft at all. They're the hardest skills.
They're the hardest ones.
They're the ones you need most in industry and things like that. Thanks for having spent this amount of time with us. Good night.